We chose this because it was fascinating to see standing waves on a loop, and Mr. Anderson was inclined towards some group taking this, so we decided to take it. Our aim was to investigate whether NF1 is equal to Fn in a vertical loop. I'd say our investigation was successful, although we faced a lot of problems. We had good results, even though it was hard to see vibrations in the fourth and fifth harmonics due to the rigidity of aluminum. Now we will show you how the loop vibrated in the first, second, third, and fourth harmonic. Correct? So this is the fifth harmonic, but the string is 2, the wire is...
To understand the concept of standing waves, first we must understand the concept of reflection on a fixed end, linear. So over here we can see a diagram where a wave pulse goes in as a crest. Since it's a fixed end, it reflects back as a trough. Now, what is a standing wave pattern? A standing wave pattern is a vibration pattern created within a medium when the vibrational frequency of the source causes reflected waves from one end of the medium to interfere with incident waves from the source. The interference occurs in such a manner that specific points along the medium appear to stand still. This is what a standing wave looks like. A wave gets sent from one side and gets reflected from the other side, and these waves superimpose to create the wave shown in black. Since there's only a specific vibrational frequencies that this happens in, these are called fundamental frequencies, f of n. Over here we can see the first fundamental frequency, which is one standing wave, f of 1, and the formula for that. Over here we can see a formula, v is equal to lambda f, and we can translate that into f is equal to v over lambda. If we use the same logic for this rugby ball, for this one standing wave, we can say f of 1 is equal to v over 2l, because 2 rugby balls cause one wavelength. Over here, for f of 2, we can derive the formula f of 2 is equal to v over l. For f of 3, we can derive the formula f of 3 is equal to v over 2/3 l, which is basically 3v over 2l. And for f of 4, we can derive the formula 4v over 2l. So from here, we can get a general formula, f of n is equal to mv over 2l, and that can be translated into f of n is equal to n times f of 1, because remember, f of 1 is v over 2l. That's exactly what we have here. Now, for the concept of the lab that we did, which was a vertical standing wave, as seen here, we chose to argue that f of n will be equal to f of 1 times n, the fundamental frequency times n. Structure followed by these waves comes back to the same fundamentals of reflection on the fixed end, linear. However, over here you can see the wave pulses get sent in both directions and reflected back in both directions. However, that should not take away from the fact that specific frequencies cause such static waves. So the value for frequency may differ due to the circular shape. However, f of 1 should still equal f of n should still equal f of 1 times n, because the concept and structure followed by it is still basically the same. Over here in our experimental data, we can see a table of a number of standing waves in frequency. Over here we can see, according to our graph, the equation for our graph is y is equal to 11.33x plus a very small number, which we really shouldn't need to count. If we relate the formula of the graph back to the formula f of n is equal to f of n times 1, we can see f of n is y, f of 1 is 11.33, and n is equal to x. And all the values to obtain a standing wave comes from the same fundamental frequency, f of 1, 11.33, as seen here.
So here, we have 3 hours left for this lab. What are you doing?
Oh no, hurry.
Ah, it's fine. We've been doing this the unconventional and innovative way. The whole lab throughout. I'll show you how. First thing is, what we did was, it's very hard to keep this thing upstanding. So what we tried taping it, but we didn't get the proper frequency. So what we did was we flipped the whole frequency generator like this, to like this. Then what we did was we stacked up weights like this. So we got a stable reading. And this thing, we had someone hold it out. Oh, we need more weights. We had someone hold it out like this, just in case it didn't fall, because it did once. So while this was vibrating, we couldn't really see it properly. So what we did was we made a white background just so we could see the rugby balls or the standing waves properly. In addition, we also turned the lights off and we used the flashlight to get a good shadow reading of the whole thing. So while it was vibrating, we could see the rugby balls. Another thing we did, I'll show you how we made this wire in the first place, because it was very hard to get the optimal wire to make the round thing. We had so many choices. Look at all these, and Mr. Anderson recommended us the copper ones, these ones, because they would give us like a very clear standing wave, but then they weren't very stable, and we couldn't figure out a way to like keep it untilted and straight. So what we did was we went to the bhaiya there and we asked for aluminum wires, because they're very rigid and also like have a very low density. So it's like very optimal for this. So how we shaped this was, so I'll show you with the copper wire. What we did was we took this bowl that the guy over there provided us. We took it like this and we tied it like this, but aluminum is really hard and it's very hard to tie it after this. So what we did was we took these tweezers and we just tweezed it like this. I'll show you here. I'm gonna destroy this one. Like this, you could easily bend it like this with the tweezers. So that's how we formed this, the rigid end here. We taped it just in case it doesn't tilt, and it's very like firm here. We did face quite a lot of problems because the aluminum wire, even though it's very rigid, it tended to snap because of the how I turned it around and how these sharp edges, it affected the whole thing, because you could see like the aluminum was coming off like shreds. So at one point we were playing really loud music and the thing snapped completely. This happened like 2 or 3 times set up, because we took this whole thing and we flipped it around like this. And we set up like a whole cardboard thingy. I'll show you in the video. But then we figured out that this thing was coming, this part right here, it was coming in the way, so we couldn't do it. It was a total failure. Mr. Anderson usually recommends us to have the 5 data points. We did have until 4. We had clear ones until 3, but then when it got to 4, the rugby balls weren't as visible because of how rigid it is. So you can really see. But then unless you like zoomed in onto the whole standing wave, we couldn't really see the 5 rugby balls because the frequency wasn't strong enough, I guess, and the material's not ideal. If we had used copper instead, I'm pretty sure we would have got it because it's more lightweight. So I'll show you how we set up the whole thing. What we did was we took power amplifiers, because if we just use normal generators, it won't be loud enough. We have the Vernier software technology, which we connected to the power amplifier speaker, which actually produced the frequency. Okay, as you can see, it's a standing wave. You can see 3 harmonics, even though it's not very stable, but this is how we generated the frequency. And you can change the amplitude. as you can see, the
Finally, my advice for future students is don't twist the aluminum wire too hard as it would snap when it reaches resonance, and use thick wire instead of thin wire.